Now we're going to be first learning about the intermolecular forces. So up until this point, we've learned about, well, we'll go up here. We learned about two types of forces. The first, which I didn't really talk about what they're called, but they're called intramolecular. So the only difference here, intra. This means between atoms in a molecule. So if you have the covalent bond between H and O in water, that's called an intramolecular bond. Anything that's ionic or covalent. So we've beat the dead horse with that. We know all about them. Then we're going to learn about intermolecular. So let's say you have a bunch of water, and all those water molecules are being held together by some force, right? Because if you push down on water, it will form around your hand. You can't take a single water molecule out. If you have maple syrup, it's very viscous. Why is it viscous? Why do different substances have different boiling points than others? Why do different substances have different vapor pressures? Meaning, like if you have experience with like nail polish remover, if you spill that, it wipes away very quickly, and like you don't even have time to wipe it. It kind of just fades. It goes into gas form. That's called vapor pressure, or that's called evaporation. But that's due to the vapor pressure, which is due to the intermolecular forces. So how these molecules interact with each other and the electrostatic interactions involved. That's what that is. And then we're going to be going off of that to learn more about these different solids and liquids, and then how the phases interact with each other. But so we know intramolecular bonds within molecules. So you have covalent bonding, ionic bonding, and then we're going to learn about intermolecular between the molecules. So within versus between the molecules. Okay, so changes in state. We are familiar with the changes in state. So solid to liquid, and all these changes in state, keep in mind, are physical. So the molecules will stay intact. That's a key thing. So when you're boiling, what's exactly happening? I think I've said this before. When you heat something up, and so you heat up water, you're breaking some bonds there in order for the water to be released as a gas. You're not breaking covalent bonds between hydrogen and oxygen. When you boil water, you're not making hydrogen gas and oxygen gas. You're making water molecules, water vapor. And that water vapor is made of just H2O, but it doesn't have the hydrogen bonds necessary to bond to other H2Os. That's what the heat is doing. It's breaking those hydrogen bonds by making the molecules move very rapidly, which we know about from our gas laws and our general information about boiling. Okay, so we'll be talking about how this relates to pressure also later. So when the more energy you add, eventually the gaseous state is reached. More energy required to overcome covalent bonds and decomposing water as opposed to component atoms. Yes. So basically, we'll learn how the more of these intermolecular forces you have, the higher your boiling point is going to be, and also the higher your melting point is going to be. Basically, the more energy it would take to disrupt these bonds, meaning if the stronger they are, the more energy it will take. And let's start with the strongest type. So the first type of these intermolecular forces is called the dipole-dipole, right? And there's many different types of dipole-dipole. And the general definition is it occurs between polar molecules. So we know based on the difference in electronegativity between the bonds and also the symmetry of the molecule, which ones are polar and which ones are nonpolar. So nonpolar means you have a symmetrical distribution of electronegativity, such as methane, or let's give a better example, like tetrafluoromethane, where this is a nonpolar molecule. Even though the bonds between C and F are polar, very polar, they cancel out equally and oppositely in every direction because it is a tetrahedral arrangement and it is symmetrical. So for polar molecules such as HCl, you have, or polar molecules that have a difference in electronegativity, that's great. You would have a pretty strong dipole-dipole interaction, meaning the dipole is formed by each molecule, meaning one side of it will have an electron pulling group, meaning a more electronegative group, and the other side will have a less electronegative group, which would be, we call it electron deficient. And then the chlorine will be electron rich. So if you have millions of these HCl's all going next to each other and interacting, the negatives from the Cl are going to interact with neighboring molecules of HCl for the positive end of the hydrogen. This bond is a dipole-dipole, this interaction. This interaction is a lot weaker than the covalent bond that brings them together, the H and the Cl, but it's still pretty strong. And you can have stronger dipoles depending on how negative and how positive something is. So the strongest dipole would be like HF, because the H from one molecule versus the abundance in negativity or the sheer amount of electronegativity coming from fluorine, which is the most electronegative atom, will make a very electronegative or very negative charge on the fluorine, which would bring these even closer together and cause a stronger dipole. So that's the fundamental idea of a dipole. Now there's different types of dipoles too. And you see it's weaker than ionic and covalent. So approximately 1% as strong as ionic or covalent, but they form these big lattices between the different molecules, which is actually pretty strong overall, depending on the strength of the dipole. The strength of the forces decreases as the distance between the poles increase, obviously. So if you get further away, the strength of the dipole-dipole decreases. Now, a specific type of dipole, so this dipole-dipole can happen with any polar molecules that are in the same mixture. So this is why polar molecules dissolve only in polar molecules. And we'll learn about that later, but I'll just say that definition now. Polar likes polar. So things that are polar dissolve in water and other organic, or sorry, not other polar solvents. And there's a bunch of polar solvents out there. And things that are non-polar don't dissolve in polar because they lack the same type of intermolecular forces. But that's just the main idea. Now, going in depth about one of these intermolecular forces, one of these dipoles is called the hydrogen bond. So it's the strongest dipole-dipole force. And it's so strong, it's probably at least double as strong, depending on what your hydrogen bonding. So that's why we have it in its own class. And it's prevalent in molecules that have, it's very specific too, to molecules that have hydrogen and one of these three highly electronegative atoms, meaning oxygen, fluorine, and nitrogen. Only those three. Sometimes there's hydrogen bonds that occur with sulfur, but not usually. So these are the main three. So the way it would work is very similar to the normal dipole-dipole, but your dipoles are going to be super strong. Just like I mentioned this example with the HCl, what if it was HF? That would be a lot stronger. So water is a perfect example of that. You have the partial negative charge on oxygen, the partial positive charge on hydrogen, and the hydrogen from one water will make this hydrogen bond or the dipole-dipole bond with a neighboring oxygen. And this will happen throughout the entire liquid, making liquid water. And that's how it forms. Or even ice, same thing. But in ice, the bonds are a little bit more relaxed. That's why ice has a larger volume than the liquid mass of the same mass in liquid. But anyway, okay. Any questions on that? On on dipole-dipole, on hydrogen bonding? What's the difference between them? What's the same? They both have the same principle, but hydrogen bonding is a lot stronger. And it only occurs with one molecule having hydrogen and bound to one of the following O, oxygen, fluorine, and nitrogen, and the other molecule, same thing, having one of those things. If you have this, HCl, which is polar and easily dissolves in water, interacting with the oxygen and making this dipole-dipole, would that dipole-dipole be a hydrogen bond? I mean, on one side you have, it's bound to oxygen, right? It's one of these highly electronegative atoms. So what do you guys think? Simple yes or no. Is it going to form a hydrogen bond? Good, Harrison. No. Oh, it's okay, Isaiah. So HCl and water will not form a hydrogen bond because HCl is not extremely polar enough, meaning it doesn't have one of these three atoms, oxygen, fluorine, and nitrogen, bound to the hydrogen. So this net dipole, let's say this would be, obviously the Cl would be negative and the hydrogen would be plus, but it won't be as polarized That's what we call it. That's where the word polar comes from. It won't be as polarized in the negative direction than if you had fluorine, nitrogen, or oxygen over here. So it'll be a weaker polar molecule than water, meaning it will still form a dipole, but it won't be a hydrogen bond specifically. Okay, so any questions on that? No? All right. All right, so then we have the next type. So we already covered dipole-dipole. That's the strongest intermolecular force, is the hydrogen bond, and then underneath that is the other dipole-dipoles. Well, there's actually some that are more stronger, but okay, out of the dipole-dipoles, because it gets weird. When you get to biochem, it gets weird. But out of the dipole-dipoles, you have hydrogen bonds are the strongest. Then you have the normal ones, which are just any other polar molecule, which are also strong too. Now let's get into the weaker ones. You have these London dispersion forces, and it exists between noble gases and nonpolar molecules, meaning anything that's inert, meaning that doesn't want to react with anything, such as CO2, neon, helium. Remember we talked about how based on the molecular orbital diagram with the, remember that thing that you didn't like with the arrows going up? That neon 2 and He2 would never form an atom or never form a molecule together. And that's because they are nonpolar, and not because they're nonpolar, but they don't want to interact with each other with anything, and they're inert. So they're still going to have a force. That's the thing. This force is called London dispersion. And what this means is, keep in mind, this is extremely weak. It is a very transient force, meaning it comes and it goes. It's very split second and it's short-lived. So here's how it happens. You have, let's just say, this is the example I use. It's the best way to represent it, but there's other ways this could occur. But let's say you have two of these blobs that are, it could be molecules, or they could be atoms. In this case, it says they're atoms, but don't focus on that. You have them hit each other. They would have a collision. For a split second in that collision, the protons or even the electrons move in one of the atoms from the front to the back, or to the back to the front. Kind of like if you stopped your car short, you would obviously go back. The electron, think about this atom would hit this atom and its electrons will go back. When they go back for that split second, this is like microseconds to nanoseconds, it creates what we call induced dipole. This collision makes an induced dipole, which gives the front of the atom a partial positive charge and the back of the atom a partial negative charge. This partial positive, partial negative then influences the adjacent atom, which didn't change, for all of its electrons to face the positive end over here, and then the back will then therefore be a positive end because it is electron deficient. All the electrons are in the front. So it makes this what we call induced dipole by a collision, by some kind of energy change. It could just happen spontaneously, honestly, but the collision is the best way to think about it because it's physical. When you physically hit something, there's going to be a reverberating force going backwards. This reverberating force shifts the electrons and also the protons in a non-symmetrical way, let's say to the back of the atom with the electrons, making a very short-lived interaction that once these atoms, remember, they're all moving very fast. So once they move fast, this bond isn't strong enough to bring them together forever, but they, and eventually they just break apart. And yeah, it sounds like it could be in a song, like a love song, what I just said. But anyway, any questions on that? So it's induced dipole. It's very short-lived, and it has a short-lived attractive force. And then these are moving fast, so the distances between them become greater and greater, and then the dipole dissipates. Okay. So chemical changes. We know what this is. So physical changes, we know we're changing. Basically, we're not going to be cutting anything in half in this case. We're just going to be talking about phase changes, meaning the boiling sublimation, decomposition or deposition, melting, freezing, things like that. And then chemical changes, we know it's the formation into different substances. So we understand that already. We understand what chemical changes are. We understand this already. A lot of this is just like extra words. So the strength of the induced, oh, actually this one's a different one. So, okay, my bad. You can have a combination of these interactions. And there's actually one we didn't talk about. And is it even covered in these slides? We should talk about it. All right, I'm gonna talk about it. So, and this kind of gets into the point. You can have a combination of these different intermolecular forces, the main two, meaning London dispersion and dipole, but there's also another one that is a combination called the ion dipole. And we see this a lot. Now, an ion dipole is pretty strong because an ion has a definitive charge, plus or minus, and it's always that charge. It's not a partial charge. You know how in covalence we use partial charge for polar molecules? There's no partial charge, it's just a charge. Therefore, it's stronger. So we see this all the time when we dissolve salts in water. So when we dissolve salt in water, you have Na+, you have the oxygens, that's the minus oxygen from the water, minus oxygen from the water, minus oxygen in the water, and they kind of group around and they rip apart the Na and engulf it. This is what solubilizes or dissolves the Na. And then similarly with the Cl minus, you end up with the positively charged hydrogens that are interacting with water. Or sorry, the positively charged hydrogens are interacting with the chlorine. So this is a combinational effect. I mean, an ion dipole, it's pretty strong. It's, now good question, is it stronger than hydrogen bonds? It's about the same, the ion dipole. It's about the same strength as hydrogen bonds. So it's pretty strong, but it involves a real ion, that's why. If you have, in this case with water, it would be actually stronger because you'd have an ion and then the other dipole is actually water. If the other dipole is a hydrogen bond forming molecule, then that ion dipole would be stronger than if it was something that's weakly polar, let's say HCl. Okay, so that's the third technical type. Then we have a fourth one, which is called the dipole-induced dipole. So let's say you have a polar molecule and a non-polar molecule that come close together. Don't worry about copying everything down. Let's just look at the picture. So if you have a permanent dipole that has a plus and a minus, it comes in close contact to a non-polar molecule like a gas, like N2, for example. What happens is, because the permanent dipole comes close by and the minus is over here, the electrons in the nonpolar molecule are going to want to shift this way. They're going to want to shift to the back to get away from this B end, the negative end. This is negative and this is positive if you can't see. So they want to get away, the electrons in the nonpolar molecule want to get away from the B end. And what that's going to do is it's going to temporarily shift the electrons. And that shift in electrons induces a dipole creation in the nonpolar molecule, and the permanent dipole is in the polar molecule. So that can happen too. And this is stronger than just a normal London dispersion force, but it's weaker than the other ones, obviously, because you're involving a nonpolar molecule. Generally, nonpolars have a lot less of the intermolecular forces, a lot weaker intermolecular forces than polar. Any questions on those? No? All right. Moving on. All right. So let's do some questions. So which of the following is the strongest intermolecular force experienced by noble gases? What do you guys think? Noble gases, that's a key word. Ding, 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 we have an answer. We have two answers. A, yes, LDFs, London dispersion forces, right. Because that's the only intermolecular forces that are going to be experienced by noble gases, because they're inert, they don't want to react with anything. They'll have this transient induced dipole. And another thing is, technically, in biochem or in maybe orgo a little bit too, ion is also a type of intermolecular force, but we don't cover that in this book. But basically, you can have organic molecules that have an ion that interact but don't make chemical bonds with another ion that's on like a protein or on a cell or something else. But you can have an ion without actually making an ionic bond. It's weird, but that's a thing. That's why we don't cover it in the textbook. Okay, next one. Which of the following species exhibits the strongest intermolecular forces? So I'll give you a second and then we'll go through each one. Any answers? It's okay to be wrong. Oh, we have A, we have B, we have maybe the A was from before. So we have B, B, and B. And yes, the answer is B. Oh no, maybe because you see it on the bottom there. Uh-oh. No, I'm gonna cross it out. I can't cross it out. Whatever. Okay, fine, you see it. It's B. Yes. Let's go over why. So that's most important. So CH4, we know the Lewis structure is gonna look like this. It's tetrahedral, everything equals and opposites, nonpolar, not strong intermoleculars. N2, same thing, triple bond like that, nonpolar. CO, it's gonna be pretty polar, but it's gonna be polar, but we'll leave it there. HE, noble gas, not polar, or not, it just goes through van der Waals. Then H2O we know is super, super polar. So comparing it to CO, H2O is gonna be a lot more polar. So it will have the strongest intermolecular forces, which are hydrogen bonds. Okay, now what types of intermolecular forces are exhibited by methane? Kind of already went over this. Which ones? Which one or ones? We have D, yep, good. D is the answer. Oh, because it says it down there. I'll hide that. So yes, D is the correct answer, London dispersion, because CH4 tetrahedral, it's nonpolar, so it's only going to go through nonpolar forces, such as London dispersion. Everything else is polar. Now, here's something interesting. Technically, everything has van der Waals, or I call it van der Waals. Van der Waals and London dispersion are the same thing, but van der Waals, we call it that in biology. So London dispersion forces are in every molecule. Even if it has hydrogen bonding, it still has London dispersion forces, but they are so negligible in comparison to the strength of the hydrogen bond, we could ignore them. So just keep that in mind, that the induced dipole model, the London dispersion force, is always present, but it's when you have a lot stronger bonds there, or a lot stronger interactions there, it's not prevalent. It's not the most prevalent one. All right, next one. This one you don't have the answer on the bottom. So which intermolecular force is the strongest? Oh, this one's easy. Which one? You got this. Which one? Well, okay, so A is a good start. It's not wrong, but you have to be more specific. So yes, C is the most specific answer. Hydrogen bonds are the strongest form of dipole-dipole. So dipole-dipole, again, you have polar molecules, polars, whatever. London dispersion is nonpolars. And then hydrogen bonds are polars, but they have to contain H with one of the following of O, N, and F, or FON, or NOF, however you want to think of it. There has to be molecules that have, let's say, like NH3, H2O, HF, things like that. Okay. Another one. All right, this one's good. So this one we didn't really cover yet, but I will talk about it soon, but it's another important concept. So and you can kind of do intuition. Which of the following has the lowest boiling point? Do you think? They're all organic, they're all nonpolar. They're all just carbon chains. This one is ethane, this is propane, this is methane, this is pentane, this is butane. Which one has the lowest boiling point? Answers, we have D and C. Okay, it's between one of those. It's either between the biggest molecule or the smallest molecule. That's what we have. So I'll a couple more seconds for answers. Another answer for C, another one for C, another one for C. Oh, that was just two. Okay, yes, so C is the right answer, the smallest one. So here's what I will write. Here's a good statement to understand, is that the mole. I meant that was a fail. All right, so the stronger intermolecular forces equals higher boiling point. And what this means is, if you have stronger intermolecular forces or more of them, I'll put stronger / more, then you will have a higher boiling point, because in order to boil or to transition phases of the same amount of molecules, you're going to have to break a lot more bonds, and you're going to need a lot more energy to do so. So if we compare a mole of methane to a mole of pentane, pentane's mass and the amount of atoms in a mole of pentane is, let's see, there's 5 atoms here, there's 17, is 3 times the amount of atoms. That means you're going to have, yeah, it's going to be all nonpolar London dispersion forces, yeah, but it's going to be a crap ton more in the same amount of molecules in a mole, because you just have, per mole, there's just more atoms. So you're going to have more atoms, more intermolecular forces, therefore a higher boiling point, meaning more energy is required to break those intermolecular forces when you have a larger molecule. And for lowest boiling point, it would be the one that has the lowest amount of intermolecular forces, meaning the lowest amount of kind of surface areas for interaction. That's another way of saying it. Okay, the lowest chance of being interacted with, because the smallest. Okay, so now let's learn a couple of more things about liquids. Or before that, is there any questions on what I just said? No? All right, liquids. So they don't really compress much. They're dense compared to gases. They have surface tension, and they have large intermolecular forces in comparison to gases. And their intermolecular forces directly correspond to 2 things. One of them is written here. One of them is surface tension. So large intermolecular forces mean higher surface tension. Also large intermolecular forces mean higher viscosity. So water is actually considered to be pretty viscous in comparison to a lot of other non-polar solvents, such as hexane or dichloromethane, that are not polar, and they're not viscous at all. Like and they have very low vapor pressure, or sorry, very high vapor pressure. We'll mention vapor pressure later on. So something that these liquids can go through in polar liquids is capillary action. So capillary action is the rising of liquid through a narrow tube. So who's ever seen capillary action before? And you can have little glass capillaries. They're used in labs a lot. I use them all the time. And basically, you can dip them. It doesn't really work with a straw. It's too thick. But if you have a really thin chamber, thin glass capillaries, narrow tube, any kind of really incredibly narrow tube, you put it into a polar liquid. Even if a liquid has a little bit of polar molecules in it, you put it in, and without submerging it completely, the liquid kind of crawls up the side or on the inside. It crawls up on its own. It looks like that someone would need to be like sucking it in like a straw, and it would just go up all the way by itself. The reason why is capillary action. And that happens because of the intermolecular forces, and more specifically, the adhesive forces between the liquid and the walls of the container. So there's two types of forces that happen when you put a liquid into a container. There's the cohesive forces, which are the intermolecular forces among the molecules. So it's the things that are keeping them together. This directly relates to the surface tension. So for water has a relatively high surface tension. If you spread your body weight enough, you can walk, you can float. There's a reason for that. Well, it's because of density, but there's a reason why if you put your hand very gently on water, it doesn't break the surface immediately. The water kind of balances it, and you can kind of compress the water a little bit around your hand until you break the surface. That's a relatively high surface tension, the tension required to break the surface. So that's due to the cohesive forces between the water molecules. Then the adhesive forces are between the liquids and the sides of the container. And we can see that here, where we have adhesive forces on the glass of the molecules to the glass are stronger than the cohesive forces between the molecules and each other. This is what makes them meniscus. This is why water and every other polar solvent has a meniscus, is because the glass is going to have stronger cohesive force or adhesive forces with the water molecules, and they'll kind of climb up a little bit. They won't climb up all the way like capillary action, but it's the same idea, but just a little bit. Then you have cohesive forces that if they outweigh the adhesive forces, meaning the way the liquid climbs up the side, you'll actually have a convex meniscus. And this is with very non-polar solvents that don't interact with like the silica or the partial charges. There's some charges in the glass that don't interact with some of those charges. That's going to be a very non-polar solvent. And that's going to be a convex meniscus. That's also possible. Okay, then viscosity. So viscosity is the measure of a liquid's resistance to flow. And again, you can imagine, and also I'm building a lot of associations here, but they all kind of make sense if you know about intermolecular forces. That's why we started off with that. And for viscosity, liquids with large intermolecular forces and complex molecules tend to be highly viscous. So like glycerol, that's a long molecule with a lot of OHs on it. And grease is a long chains of molecules that have pretty strong intermolecular forces because they're large. So that's a thing. That's a thing. Well, yeah, that's true as well. So any questions on that? The glycerol looks like this. And you can have chains of glycerol that are just more of those. And you have a lot of OHs bonding to a lot of other OHs and hydrogen bonds being formed and a lot of different things going on. Or a lot of dipoles being formed as well. So it's going to be a pretty strong overall structure. And there's thousands. These chains could go on. Okay, so now any questions on liquids, on what we learned about liquids so far? No? Okay, so for solids, there's a lot. So the textbook covers a lot, and it's kind of too much, and it's a little bit more than we need to know. So we're going to learn the important stuff, and then there's a lot of non-important stuff going over different types of steel and things like that. I left the slides in there for you, but we're not going to cover them drastically. I'll just read them off. But you can, depending on what type of engineer you are, if you're a civil engineer, maybe you need to know about that. But I'll talk about it in brevity. Anyway, so solids. There's two types of solids. There's amorphous and crystalline. So amorphous is just a bunch of stuff, a glob, the plum pudding model, if you remember that. But it's just like a bunch of crap in there, and there's no structure, there's no organizational structure to the atoms. A crystalline solid, on the other hand, has a highly regulated arrangement, and this forms a lattice. And we've already talked about lattice energy, meaning the energy required to break a crystalline solid or break a lattice of a structure. And also this can create a unit cell, which is the smallest repeating unit of the lattice. And we could figure out a lot of different measurements of the lattice and the amount of atoms and moles that are in the structure based on the unit cell configuration. So two types of solids, amorphous, crystalline. Okay, so here are the way these crystalline solids could behave. And I'll make this a little bit bigger for those of you who are online. There are three types of these unit cells. Don't look at the lattice too much because that's too confusing. But basically, these unit cells make up the lattice. And it looks like in every picture, there's 4 unit cells in a bigger cube that make up this lattice to give you an idea of what it looks like. And there's 3 types of these unit cells. And it's important, we're going to learn about each one. It's important to know how many atoms are in each one, because they're based on the sizes and the different arrangements in every compound that the atoms like to take. They could be more closely packed together or more widely dispersed. And we go kind of in an order of low density to high density. So you imagine molecules that be packed like this are going to be way more than ones that pack like this. Okay, so the first one's called a simple cubic. Now, the simple cubic is, and keep in mind, we're looking at everything inside the cube. So I'm going to ask a question. This might be tough. I'm going to write number of atoms here. We'll make a chart. How many atoms do you think are inside the cube? So inside the cube. Now, on the outside of the cube, you have part of it, right? But what's inside the cube? If you look at each corner, what's inside the cube? We have an answer. 8. Not 8 atoms, but there's 8 sides, right? And there's 8 chunks of the atoms that are taken off. So it's like a pizza slice, but a 3-dimensional pizza slice. Oh, it's okay. Yeah, atoms. Yeah. So right. So what is the 8? I like 8. So we'll talk about 8. So there's 8 corners. Each corner has a chunk. What is the fraction of that chunk in the whole sphere? You have to use your engineering mind a little bit. What's the fraction? Come on, I need a fraction. Anybody? 1/8. Thank you, Harrison. Good job. So 1/8. So this is kind of chunking, getting a chunk of 1/8 of each atom. And since Mancy said there's 8 of them, 8 times 1/8 is 1 atom. So in this unit cell, the simple cubic, it's the most simplest one, right? The way they arrange is in this, and keep in mind, this simple cubic is just a 3-dimensional cross-section of one of the lattices, and there's 3 of them based on their complexity. So in this simple cubic, there's 1 atom that's inside the cubic, and these could be stacked millions and millions on top of each other. Okay, so next is more complex where the density increases. It's called a body-centered cubic. So it's body-centered because This is tough to see because there's a body in the middle. Okay, this one, yeah. Okay, we're gonna go to the next slide because these are more tough to see, but this one was not that bad. All right, how's this? No, not that. This. That's better, right? Yeah, so that makes more sense. So polonium is an example that goes through a simple cubic. And you see it's one atom. This is an eighth, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, 8/8. Then this is the body-centered cubic. So body, not bony-centered, body-centered. And you can see there's one complete atom in the middle. It's body-centered. The body of the atom is in the middle. And then you have the same thing as a simple cubic. You have the 8 corners. So it's going to be one atom plus the 8/8, which is 2. And then the last one is called the face-centered, which is the most complex one. And I'm going to let you, oh, there's 4 atoms, damn it. Okay, who can explain to me why there's 4 atoms? Or can you find the atoms? Find the 4. Anybody? You can speak. There's 4. Okay, there's 4 halves on the faces. That's true. There's not one hole in the center. There's 2 in the center, 2 from the corners. Not 2 from the corners. Plus original from the corners. Yeah. Oh, you're kind of, I mean, you're getting there. Harrison's got it. You're on a roll today. 1 from the corners plus 3 from the faces. That's exactly it. Because remember, a cube has 6 faces. So what that means is each pair of faces, meaning this one and the bottom, this one and over here, this one and over here, those are each of those pairs are going to be atoms. So from those face-centered parts, those halves, there's going to be 3 atoms, plus the one that we've seen in all of them that it's on the corners, the eighths, the eighths. So it's going to be 8/8, which equals 4. Okay, so you could be like, hey, professor, what do we need to know about this? Why do we care about this? So there's going to be questions on the homework and maybe on the exam that tell you, oh, the atom's radius is a certain thing. What is, and it uses it arranges in a face-centered cubic. What is the volume of that cubic? Or what is the lattice? What is the volume of that cubic? Or no, so what is the volume of the lattice that has 4 cubics in it, or has 4 unit cells in it? So for that, you have to keep a couple things in mind. So for, like, let's say we did a simple cubic. The radius of the atom would be this. There's 2 of them. 2 radiuses of the atom is one side of the cube. Well, you take it cubed, multiply it by itself 3 times, and you get the volume of the cubic. For this one, these ones are a little bit more difficult, and there's equations, but we don't need to go crazy with that. Did they talk about the equations? I don't think so. Okay. All right. Any questions on the cubics? There's maybe only 1 or 2 questions on this, on the homework. So, okay. Next, more about solids. So these are all crystalline solids, right? Because we're talking about these cubics. They're fixed 3-dimensional arrangements that are arranged in a fixed way, in a certain way. They're not just sloppy. So they're crystalline. And there's 3 types of crystalline solids. One of them is ionic, which is just by salts, like NaCl, ionic solid. Molecular solids that are covalent bonds, such as ice. and atomic solids, which are just an atom form, elemental form, such as graphite or diamond, for example, the carbon that's put together, or even like sulfur powder. So anyway, here's diamond. You have this specific arrangement, and it kind of looks like a baseball cap. Like this is the bill up here, and then yeah, and then you can draw like the back of it, kind of. Yeah, but I mean that's just like the best way to draw the three-dimensional arrangement. So that is the atomic solid. Then you have the ionic solid, and here's the molecular solid, where you have ice, where it's just waters in a crystal lattice that are stacked upon each other, which makes a snowflake. Okay, cool. All right, so here we go on how we figure out the number of atoms. We did that already on the face center cubic. Okay, so here's what we're not going to really cover too much on, because it's not going to be covered on your exam, and it's a little bit superfluous, but I did leave it in there in case some of you are interested to look over on your own. So alloys. So what an alloy is it's something that contains a mixture of elements, usually with the base of a metal. There's usually at least one metal in there. And there's two types of alloys. There's a substitutional alloy and an interstitial alloy. So a substitutional alloy means it has mainly a metal, but it also puts in there other metals of different types in smaller quantities. And bronze is a good example of that. What else? There's a lot of them. Brass is a good example of that too, where you have like zinc is mixed in there with copper and things like that, and tin. So there's a bunch of different ones. And then interstitial alloy, I'll show you some examples in the next slide. Interstitial alloy is when you have sometimes smaller atoms that could be usually not metals, like carbon, that are mixed in there to make a really strong substance. So here's the example. So here's brass. You have copper and zinc. And then if you add, to get bronze, you add copper and tin, I think, based on RuneScape. Those of you who played RuneScape when you were little. But yeah, so anyway, those are both types of these substitutional alloys. Then you have interstitial alloys like steel. There's many different grades of steel. So here's steel where you have mostly iron, and then there's carbon mixed in there to give it some more rigidity and to give it better properties, less flexibility, things like that. So here's just some grades of steel. Mild steel, less than 0.2% carbon. Medium steel, like 0.6%. High steel, 1.5%. So there's different uses for them. Yeah, medium steel uses in rails. And why don't they use high steel? I'm not a civil engineer, so I don't know this answer, but why don't they use high carbon steel in rails and structural beams? Seems like the steel that's made in like the bridges and everything, that's like really heavy duty steel. So that's there for like hundreds of years. Anyway, okay, so then you can have network solids, which have covalent bonds in them, but they're not they're not conductive because you're having mostly non-metals. So things like that, you'll have like graphite, you'll have silicon chips are a good example of that. They're not good conductors. So silicon is not a good conductor. It's a semiconductor for a reason. It conducts poorly. I mean, if you had, and there's a reason why, I mean, if you hook it up with different electric fields, you can modulate how much electricity goes through and what kind of signals you send. That's the reason why computers can't be made of just copper or any kind of other metal. It can't be made of just metal. You have to have silicon because otherwise you'd have either all the current or none of the current. You can't modulate the current, and you'd always have a short. You have diamond. So diamond looks like this again with different. This is all carbon, so it's very compressed carbon. So the molecular orbital diagram. So diamond can be synthesized. Here we go. Graphite can be converted to diamond. This is the amount of pressure. So synthetic diamonds are more expensive, or are they more expensive than regular diamonds? it's close. Well, I was actually looking this up not too long ago. It's like the blue diamond and the red diamonds are like the most expensive. And, well, they're natural. But synthetic diamonds are probably the same price, or like the best ones are probably more expensive than some of the other natural diamonds, but I could be wrong. Anyway, the reason why they're expensive to begin with, because you think, oh, why can't we make them in the lab? Why can't they just make a bunch and make them cheaper? Well, I mean, there's many economical reasons for that, but for chemistry purposes, it takes a lot of energy to do this. It takes huge machines to get up to 150,000 ATM at 2,800 degrees Celsius to convert graphite to diamond. So you need an extreme amount of pressure and extreme temperature. And this takes an extreme amount of energy and money. So even that's difficult to do. There's graphite, whatever, so hybridization. There's graphite again, so it's weak bonds between layers of carbon. Once you heat it up and put it to extreme pressures, these layers kind of go together and make the diamond lattice, which is this one. And then, let's see, glass. So usually it's when you have silica. So there's usually, glass is usually like the main component in glass is usually like silicon, and some salts are in there too. So, so it's just like a combination of like mostly inert things, but there is some charge to it from the making of the glass. You have some sodium in there, some carbonate is in there, and other types of just like weaker ions that are just floating around just to give it rigidity. So there's different types of glass. There's quartz glass and there's quartz crystal. So I mean, glass is more amorphous. The crystal so quartz is expensive. It's like a glass that has a very rigid structure, and it's used in a lot of optical experiments. So like I use quartz if we're shooting light through an organic sample, we use quartz because it won't refract any light. But if you use like this kind of quartz glass, which is just the glass, which is basically just glass, you're going to have deflection of the light, diffraction in also light scattering in like every direction. So you wouldn't get a good signal. Ceramics, I mean, we're not going to really cover any of that. Semiconductors, different types of semiconductors. A lot of this stuff is just beyond the scope of the course, but it's there. This one thing I did want to get to, here's the last real part of the chapter. I mean, it's only 7:04. So what we're going to do after is we could do homework. Yeah, I mean, I'll stay to at least 8, and we can do homework for a bit. Okay, so the last thing that's important, and it's super cool, is the heating curve. And we should all have an idea of the heating curve because we know what happens when you heat something up, right? You increase the speed of the molecules, which increases their degrees of freedom, which in turn goes from solid to liquid to gas. And then you have the heat of fusion. So that might be a new word. Heat of fusion, or enthalpy of fusion, corresponds to the enthalpy change when you melt something, or when you freeze something. So either when you freeze something, the energy is being removed because it's now colder and the molecules have now slowed down. But when you melt something, this heat of fusion is then put into the substance in order to melt it and make its bonds go faster, or make its molecules move faster and increase their degrees of freedom. So that's heat of fusion. That's an important term to know. So here's what the heat curve looks like. You have ice at very low, this is for water, of course. So you have as energy is added at a constant rate on the x-axis and temperatures on the y, you add energy of ice, eventually you get to the melting point. Then in the melting point, until all of the ice is converted to water, you have a combination of ice and water. No matter how much energy you add, you have a combination of ice and water. So even if you add this much energy to ice, for some time, the time might be shorter, but for some time it's going to be ice and water, and the temperature is not going to go above 0. Then you add more energy, you get water, 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 until the boiling point. So you can try this at home. If you put a thermometer in boiling water, even if you set the oven to 400 degrees, and you make sure you put a lot of water in there, make sure it's all boiling, the water will not get over 100 degrees. Even if the stove and the outside of the pot is 400 degrees. The water will only be 100 because you're putting that thermometer in liquid water. Liquid water cannot physically be over 100 degrees. The hotter it is, the faster it will boil out, but it's still going to be 100 degrees until it boils out. And then you can have steam for infinity. Okay, any questions on that? No? Okay. All right, so as you heat, whatever. I mean, well, not whatever. As you heat, we understand this already. Yeah, whatever. We understand that. It's just Q equals MC delta T. Melting is endothermic, right? So you need to put in energy to give those molecules that are solid and give them a liquid state or give them a increased kinetic energy state. Because when you form the solid, you lower the kinetic energy, right? So you need energy to come back in order to increase the temperature and increase the kinetic energy, which is the same thing. So here's the heat of fusion again. So the heat of fusion, this kind of just definition stuff. The heat of fusion, which is right here, which is the energy that's required to go from a solid to a liquid, is the same energy as the energy needed to go from a liquid to a solid, obviously. But based on when you're freezing something, it's an exothermic reaction, which is the heat of crystallization. This would be negative, and this would be positive. Heat of fusion is usually endothermic. But the idea is that they're both opposite. They're the same amount of energy, but the signs are both opposite when you're going from solid to liquid or liquid to solid. And then you have the heat of vaporization. So the heat of vaporization is the heat required, or the enthalpy of vaporization is the enthalpy required, or the energy required for 1 mole of liquid to become all gas. That's usually big because you're going to have enough energy there to make every liquid molecule reach its boiling point. So that would be rather difficult. But anyway, so a way you can sum this all up is based on the phase diagram, or based on the heating curve, which you have different states, you can say sublimation, the enthalpy of sublimation, which is going from a gas, liquid, solid. So it's going from a solid to a gas directly. That's delta H sub is equal to the subsections. Heat of fusion is going from solid to liquid. So that's delta HF. Going from liquid to gas is heat of vaporization. So the heat of sublimation is going from one end of the spectrum to the other. So the way you can sum that up is by knowing the heat of fusion, which is going from liquid to solid, and then the heat of vaporization, which is going from solid to liquid. Or sorry, liquid to gas, my bad. So it's important, I know as I said, a lot of delta H's, a lot of enthalpies. The important thing is that you understand what the process type, either endo or exothermic, going from each phase transition. So going from solid to liquid, what do you have to do? Input energy, endothermic. Going from liquid to gas, what do you have to do? Input energy, endothermic. Going from gas to liquid, what do you have to do? Take out energy, exothermic. Going from liquid to solid, what do you have to do? Take out energy, exothermic. The sign will be negative for those, if you're talking about the system. And then you can be like, all right, what if I go from directly gas to solid? That'll be hugely exothermic because you're going from the highest energy state now to the lowest energy state. That energy has to be released from the system. And how do you quantify that energy? All right, you can break it apart into its phase transition components, which is the delta enthalpy going from a gas to liquid, which is vaporization, well, the opposite of vaporization, and then heat of fusion going from a liquid to a solid, or that would be the heat of crystallization, but the opposite of heat of fusion. So I know it's a lot, but does that make sense? Hey, a question. Yeah. Oh, it does. Okay, cool. I'm glad it makes sense. I didn't think it would. Not because of you, because of me. And keep in mind, these heats, these enthalpies are per 1 mole. So it says it up here, but it got moved. The amount of energy required to melt 1 mole of solid. So for all these, it's per mole. It's usually, enthalpies are kilojoules per mole. Oh, and also I'll talk about it later. I'm still on video. Okay, any other questions about it? Anybody need me to wait? No? All right. So let's talk about, this is the coolest thing ever. Let's talk about this. So this is the phase diagram for water. Every substance has a phase diagram. Why is this in white? It's like the worst color to put text in. Red, here we go. Okay. So this is a phase diagram. Every substance has its own phase diagram. What it represents is on the y-axis you have pressure, on the x-axis you have temperature. And it represents the different phases, solid, liquid, and gas, that you can be in at certain temperatures and pressures. So let's talk about first what we know. At 0 degrees Celsius, or anything below 0 degrees Celsius, at 1 atm, water is a solid. It's ice, right? And look at that. 0, anything below it, and above 760 or at 760 is solid. And everything greatly above 760 and most of it below is still solid. Then at 100 degrees, above 100 degrees, we know water boils. So above 100 degrees at around 760 torr or 1 atm, you have mostly gas. So that makes sense. But there's things that are different. So there's things that what happens when you greatly change the pressure or greatly change the temperature. So pressure is really cool. What you can do is you can increase the pressure enough, decrease the pressure enough. Well, let's talk about what pressure is doing. Pressure is a force that's on the substance. What it's doing is it's physically pushing down on the substance to give it less degrees of freedom and give it less energetic motion, give it less kinetic energy. So the more pressure you have, the less kinetic energy you have. What does that mean? That means the less temperature you have, because temperature, by definition, is the average kinetic energy of a solution of a substance. So by theory, if you have an extremely high pressure, you can force things into a solid or a liquid from a gas. And that's exactly true. Because look what happens at, let's say, out here, right? Let's say this is 150 degrees. At 150 degrees at normal atmospheric pressure, ATM, 1 ATM, you have, of course, water is a gas. If you increase that pressure, what's going to happen? Eventually, it'll hit a point, and once you cross this line, this is called the vaporization curve. Once you cross it, you go into the next thing. You either condense or you vaporize. In this case, going from gas to liquid would be condensing. So if you increase that pressure, which you're pushing the gases together, you're physically pushing those molecules closer and closer together, giving them less degrees of freedom and less motion. Then eventually they will hit a critical point. I mean, not this critical point. They will just hit a threshold where they would cross over from gas to liquid. And at the same temperature, just by changing the pressure, you can go from gas to liquid. And really, you can change the state of anything just using pressure if you have enough. So does that concept make sense? I'm not done with this chart yet. I'm going to talk more about it. But so far, does that make sense, that concept? Any questions on it? Next, if you have water's a little bit different than everything else, but if you have a gas, well, if you have a solid, and it is the other, so another thing that pressure is doing, let's talk about the other end of the spectrum. High pressures, we know, can decrease the amount of freedom that the substance has. It can go from a gas to a liquid to a solid if we increase the pressure. But it's, okay, so water is different. Water, if you increase the pressure of water, it will go to the most condensed form, which in its case is liquid. So if you ever try to freeze a water bottle, right? You take a normal water bottle that looks all nice, you freeze it, it expands. Water is one of the only substances that does that. And the reason why is because of the lattice. Its crystal lattice of H2Os is in a more rigid arrangement, and they're further apart from one another than liquid water is. Even though you would think if you have liquid, it should be more expanded than a solid. But in water's case, it's not. That's why this vaporization curve is a little bit different. That's why this line, this fusion curve, goes like this. Normally they go like this. So keep that in mind. For water, it's different like that. It's different. So what is this for? Is another one? Here's a perfect example. For carbon dioxide, as you compare it to water, the fusion curve goes like that. For carbon dioxide, it's more like that. It's kind of straight up, but most substances is kind of this way. And you can play with this on your own, and you can see that if you increase the pressure, it will eventually go from liquid to solid at a certain point. Let's say you're here. If you increase the pressure enough, you'll eventually cross the threshold of solid. Or if you decrease the temperature enough. But it all depends on the substance's resistance to temperature change, which is our specific heat. So that comes into play as well. Okay, so let's go back here. Now, if we were to take off pressure, what we'll be doing is relieving the stress of the molecules. So we're all at 1 atm. If we decrease our pressure to 0 atm, and we're in a vacuum, we will either we'll turn into gas. If we are put into a real vacuum, where there's no atoms, and we'll be sucked into somewhere that doesn't have a vacuum. But theoretically, our solids, if we're put into a vacuum when there's no pressure, that means there's no forces on our surface area that is pushing our atoms together to make liquids or solids, and we will all become vaporized into gas. That's the main reason why. That's the second most important reason why astronauts wear spacesuits, because in space it's a vacuum. The two things that are the worst things in the world, in the universe for a human body, is a vacuum and the low temperatures of like 2 Kelvin. Those are, or 4 Kelvin, whatever it is in space. But those will kill us really fast. Okay, so we can see that happening in the graph. Let's say you have a solid. If you let's say 30 degree or negative 30 degrees Celsius, so it's ice, it's pretty cold. If you decrease that pressure all the way, it will actually become gas. It will actually sublimate. Water will sublimate. If you decrease that pressure, no matter however cold it is, it will sublimate, because you are relieving all of that stress from the pressure. So now the water molecules that are now solid have everywhere to go. They could just have all their degrees of freedom, and they can become a gas. And the same thing can happen from liquid to gas. You can change the boiling point of water by reducing the pressure. So by giving it leeway, by relaxing it. So does that concept make sense? Boiling point is very variable based on the pressure. That's the main idea. Does that make sense? Are there any questions on it? All right, so there's two other things. One is the triple point. I'll show you a video on that soon, or after we're done. The triple point is a place where all these curves meet, and it's a place where the solid, the liquid, and the gas can all exist at the same time. There is a triple point for water. And if you're thinking, and it would be a good thought right now, what the hell does that look like? I can't explain it. The best way I can explain it is you have water and ice in the same thing, and it's boiling. That's basically it. I'll show you a video of that. It's really cool. Now, when does that triple point occur? It is extreme. So the temperature's not extreme. It's around 30. It's actually 32.1 degrees Fahrenheit, or about 0.001 degrees Celsius. That's not too bad, but it's 4.58 torr. If you remember, 760 torr is 1 ATM. That's what we're experiencing now. So about 1 out of 200, 1 over 200 torr, or 1 out of 200, 200th less of what we're experiencing in terms of pressure gives a triple point. So you can't do this on your stove. You can't kind of like mess around with it and figure it out and find it. But you can't even do it in a lab, in like our normal Gen Chem labs, but you can do it.